In April 2022, the CDF collaboration at Fermilab in Illinois published a paper in the journal Science that should have been the most celebrated result in particle physics in a decade. The paper announced a measurement of the mass of the W boson, one of the fundamental particles that mediates the weak nuclear force, with a precision of approximately 0.01%. It was the most precise measurement of the W boson mass ever made. And the result was wrong. Not wrong in the sense of being a measurement error, wrong in the sense that it disagreed with the prediction of the standard model of particle physics by 7 standard deviations, 7 sigma. In particle physics, 5 sigma is the threshold for discovery. 7 sigma is not a hint or an anomaly or a candidate. 7 sigma, if correct, is a definitive indication that the standard model is wrong. The W boson mass measured by CDF was 80,433.5 plus or minus 9.4 MeV per c squared. The W boson mass predicted by the standard model is 80,357 plus or minus 6 MeV per c squared. The difference is 76 MeV. That is less than 0.1% of the total mass. But given the precision of both the measurement and the prediction, the disagreement is enormous in statistical terms. If the CDF measurement is correct, the standard model is wrong. Not approximately wrong, not wrong at the edges, but definitively wrong in a specific and testable prediction. The most precisely tested physical theory in the history of science would require a fundamental revision. And then the situation became more complicated because subsequent measurements by other experiments have not confirmed the CDF result. The ATLAS experiment at the Large Hadron Collider at CERN, which published its own high-precision measurement of the W boson mass in 2023, found a value consistent with the standard model prediction. The CMS experiment found values consistent with the standard model. The LHCb experiment found a value consistent with the standard model. The older measurements from the LEP experiments at CERN and the D0 experiment at Fermilab also cluster around the standard model prediction. The situation right now is that one extraordinarily precise measurement disagrees with the standard model at 7 sigma. Every other measurement is consistent with the standard model. Either the CDF result has an unidentified systematic error, which is the majority view in the physics community, or the other experiments have correlated systematic errors that cause them all to agree with each other while being wrong, or the standard model is correct and the CDF result is an outlier. This is not the clean story of a discovery. It is a genuine scientific controversy, and I want to take you through it honestly, because the controversy is itself scientifically important. The W boson mass puzzle is not the only anomaly in particle physics right now. It exists alongside a set of other anomalies, all of them individually uncertain, that together paint a picture of a theory that may be showing the first cracks. Let me start with the standard model itself, because understanding what makes its predictions so precise is essential for understanding the significance of the anomalies. The standard model of particle physics is the theoretical framework that describes all known elementary particles and 3 of the 4 fundamental forces. It was developed in the 1960s and 1970s through the work of dozens of physicists, including Sheldon Glashow, Abdus Salam, Steven Weinberg, and Gerard Hooft, among many others. It describes the electromagnetic force, the weak nuclear force, and the strong nuclear force in terms of gauge theories, mathematical structures based on symmetry groups. The electromagnetic and weak forces are unified in the electroweak theory. The strong force is described by quantum chromodynamics. Together with the Higgs mechanism, which explains how particles acquire mass, these form the standard model. The standard model has been tested against experimental results for 50 years. across an enormous range of energy scales and physical processes, and it has passed every test. Its predictions for the magnetic moment of the electron, for the mass of the Z boson, for the rates of various radioactive decays, for the production rates of particles in collider experiments, all agree with measurements to extraordinary precision. In some cases, like the magnetic moment of the electron, the agreement is at the level of 1 part in a billion. This extraordinary predictive power makes the Standard Model one of the most successful scientific theories ever constructed. But it is known to be incomplete. It does not include gravity. It does not explain dark matter. It does not explain the asymmetry between matter and antimatter that allowed the universe to be matter-dominated. It has free parameters, numbers like the masses of the quarks and the coupling strengths of the forces that are not predicted by the theory but must be measured and input. These are signs of a deeper theory waiting to be found. The W boson is the carrier of the charged weak force. It is one of 3 gauge bosons of the electroweak force, alongside the Z boson and the photon. The W boson was predicted by the electroweak theory and discovered at CERN in 1983, one of the great confirmations of modern physics. Its mass is not a free parameter in the Standard Model in the simple sense. It is predicted by the theory given the values of other precisely measured quantities, the electric charge, the Fermi constant describing weak interactions, and the mass of the Higgs boson. The precise relationship between the W boson mass and these other parameters comes from radiative corrections, quantum mechanical corrections, that involve the contributions of all the particles in the theory to the W boson mass. The top quark, discovered at Fermilab in 1995, gives particularly large corrections because it is so heavy. The Higgs boson, discovered at CERN in 2012, also contributes. By measuring all the other parameters precisely, the W boson mass can be predicted with high accuracy. The CDF collaboration at Fermilab accumulated an enormous data set over the years of operation of the Tevatron Collider, which ran from 1987 until 2011. The W boson mass measurement, published in 2022, used the full data set of approximately 4.2 million W boson events, the largest sample ever analyzed for this purpose. The analysis was extraordinarily careful, involving years of work on understanding the detector response, the part and distribution functions that describe the composition of the proton, and all potential systematic effects. The result, 80,433.5 MeV, was higher than the Standard Model prediction by 76 MeV. The collaboration was careful and conservative in their analysis, and the result survived internal review. They published it in Science with a detailed description of the systematic uncertainties. The reaction from the theoretical community was a combination of excitement and skepticism. Excitement because a 7 sigma deviation from the Standard Model, if real, would be the most significant discovery in particle physics since the Higgs boson. Skepticism because the history of particle physics is full of anomalies at high sigma that dissolved when better measurements were made or when undetected systematic errors were identified. The specific question for the CDF result is whether there is a systematic error that could shift the result by 76 MeV without being detected in the analysis. Several candidates have been identified. The part and distribution functions, which describe the internal structure of the proton and must be known precisely to analyze W boson production, have uncertainties that could potentially contribute to a shift in the measured mass. The energy calibration of the detector, which affects the measured momenta of the particles produced in W boson decay, has been studied extensively but could have residual uncertainties. The modeling of the production process involves theoretical uncertainties. The advocates for the CDF result argue that all these systematic effects have been carefully estimated and that the residual uncertainty is captured in the published error bar. The skeptics argue that the history of W boson mass measurements suggests systematic effects are difficult to fully control, and that the consistency of all the other measurements with the standard model is strong evidence that the CDF result has an unidentified error. The ATLAS measurement of 2023 found 80,360 plus or minus 16 MeV, consistent with the standard model and inconsistent with CDF at more than 3 sigma. The comparison is informative but not yet decisive because the ATLAS uncertainty is larger than CDF's. More measurements from CMS, LHCb, and potentially a reanalysis of the CDF data by independent groups will eventually provide a clearer picture. Now let me take you to the other set of anomalies that exist alongside the W boson mass puzzle. The LHCb experiment at the Large Hadron Collider is a specialized detector designed to study particles containing bottom quarks. Bottom quarks combine with other quarks to form B-mesons, particles that decay through the weak force in specific ways predicted by the standard model. The LHCb experiment has been measuring the rates and angular distributions of B-meson decays with extraordinary precision. Over the past decade, LHCb accumulated a series of measurements that, taken individually, showed modest deviations from the standard model. Some measurements of the angular distributions of B-meson decays showed deviations at the 2 to 3 sigma level. Some measurements of ratios of decay rates into different types of leptons showed deviations at similar significance. The specific pattern clustered in decays involving muons relative to electrons, suggesting a potential violation of lepton universality. Lepton universality is a specific prediction of the standard model that follows from its gauge symmetry structure. The weak force is supposed to treat all 3 generations of leptons identically. If muons are decaying differently from electrons in certain B-meson processes, the weak force is distinguishing between them in a way the standard model forbids. The LHCb anomalies motivated hundreds of theoretical papers. Models were built around leptoquarks, Z-prime bosons, and other new particles that could explain the pattern. Then in 2022, LHCb published a new, more precise measurement of the ratio RK, which compares B-meson decay into kaons and muon pairs to the rate into kaons and electron pairs. The standard model predicts this ratio to be very close to 1. The new measurement found RK consistent with the standard model. The B anomalies that had been the focus of theoretical attention for years were substantially resolved by the improved measurement. The muon anomalous magnetic moment is another long-running story. Let me develop it more carefully, because I think it is the anomaly with the strongest experimental foundation and the most interesting theoretical controversy. The magnetic moment of a particle is a measure of how strongly it responds to a magnetic field. In Dirac's theory, a fundamental spin-half particle should have a magnetic moment equal to exactly g times e divided by 2m, where g is the g factor, e is the charge, and m is the mass. For a point particle with no internal structure and no quantum loop corrections, g equals exactly 2. The anomalous magnetic moment, denoted A, is defined as g minus 2 divided by 2. For a free electron, or muon, quantum field theory predicts that A is non-zero due to quantum loop corrections. The electron interacts with virtual photons, virtual electron-positron pairs, and virtual other particles, and these interactions shift G away from 2. The leading correction from a single virtual photon loop was calculated by Schwinger in 1948 and gives A equals alpha divided by 2 pi, where alpha is the fine structure constant. For the electron, this gives approximately 0.00116. The full QED calculation, including many higher order loops, gives a value that matches the measured electron magnetic moment to 1 part in a billion, one of the most precisely verified predictions in all of physics. The muon is 207 times heavier than the electron, but otherwise has identical electromagnetic properties. Its anomalous magnetic moment should receive the same QED contributions as the electron, plus additional contributions from loops involving heavier particles. Because the muon is heavier, these additional contributions from heavy particles, including W and Z bosons, hadrons, and potentially any undiscovered particles that couple to the muon, are much larger for the muon than for the electron. This makes the muon anomalous magnetic moment a more sensitive probe of new physics. The standard model prediction for the muon anomalous magnetic moment includes three types of contributions. The QED contributions from loops involving only photons and charged leptons have been calculated to fifth order in the fine structure constant, involving thousands of Feynman diagrams. The electroweak contributions from loops involving W, Z, and Higgs bosons have been calculated to two-loop accuracy. And the hadronic contributions from loops involving quarks and gluons are the source of the controversy. The hadronic vacuum polarization contribution is the largest source of uncertainty in the standard model prediction. It comes from a loop in which a photon temporarily converts to a quark-antiquark pair. Because quarks are confined by the strong force and cannot be treated perturbatively at low energies, this contribution cannot be calculated directly from QCD in the same way as the QED contributions. Two methods have been developed to evaluate it. The data-driven method uses the optical theorem to relate the hadronic vacuum polarization to measurable quantities. Specifically, the hadronic vacuum polarization can be calculated from experimental data on the cross-section for electron-positron annihilation into hadrons at low energies through a dispersion relation. This data has been collected by experiments at electron-positron colliders in Novosibirsk, Frascati, Beijing, and elsewhere over the past 4 decades. The method has been used since the 1970s and has been refined continuously as new data became available. The lattice QCD method computes the hadronic vacuum polarization directly by simulating QCD on a 4-dimensional space-time lattice. The quark and gluon fields are represented as values on a discrete grid of space-time points, and their dynamics are simulated using algorithms that sample the space of field configurations according to the QCD action. The computation is extremely demanding, requiring access to the world's most powerful supercomputers and months of running time. In 2020, the Budapest-Marseille-Wuppertal collaboration published a lattice calculation of the hadronic vacuum polarization that gave a result significantly higher than the data-driven calculation by approximately 2.1 standard deviations. The combined effect is to reduce the discrepancy between the measured muon anomalous magnetic moment and the standard model prediction from about 4.2 sigma to about 1.5 sigma. If the lattice result is correct, the muon anomalous magnetic moment is no longer evidence for new physics. The community has been working intensively to understand why the two methods give different results. The CMD3 experiment at Novosibirsk published new data in 2023 on the low-energy electron-positron cross-section that is inconsistent with the older data used in the data-driven calculation. The CMD3 data supports a higher value for the hadronic vacuum polarization, more consistent with the lattice calculation. This finding, if confirmed, would suggest that the older data has a systematic error and that the data-driven prediction has been underestimating the hadronic contribution. The resolution of this controversy will require new measurements of the low-energy electron-positron cross-section from multiple experiments, new lattice QCD calculations with different methods and discretizations to test for systematic errors, and theoretical work to understand whether the data-driven and lattice methods are truly computing the same quantity in the same way. This work is ongoing. The muon G2 experiment at Fermilab is expected to publish its final results from all 4 years of running, which will provide the most precise measurement of the muon anomalous magnetic moment ever made. But even a more precise measurement cannot resolve the controversy if the theoretical uncertainty from the hadronic vacuum polarization remains at its current level. The particle that should not exist, if any of these anomalies is real, is not a particle directly detected at a collider. It is a particle inferred from deviations in the properties of known particles present in the data but not visible in a direct production and decay signal. Finding it directly will require either higher energy colliders or more sensitive searches at existing colliders. The current moment in particle physics is one of the most interesting and most uncertain in the field's recent history. The Standard Model is not broken. It continues to make predictions confirmed at extraordinary precision, but it shows signs of stress at specific, precisely measured points. The W boson mass anomaly from CDF, the muon anomalous magnetic moment, the remaining hints in B-meson physics, none of these is a confirmed discovery of new physics. But none has been definitively explained within the Standard Model either. The pattern across these anomalies, the W boson mass from CDF, the muon anomalous magnetic moment at Fermilab, the remaining hints in B-meson physics at LHCb, is worth examining as a whole because individual anomalies can be dismissed more easily than patterns. Every one of these anomalies involves measurements that are harder to perform and to control systematics for than typical LHC searches. The W boson mass requires understanding the detector's response to the lepton momentum to better than 1 part in 1,000. The muon anomalous magnetic moment requires knowing the muon's momentum in the storage ring to parts per million. The B anomaly measurements require precisely modeling the production and decay of B-mesons in a hadronic environment. In each case, the challenge is not detecting the signal but controlling the background and the systematic effects. This is the nature of precision physics in the modern era. The Standard Model is so good that to test it, you have to measure things to extraordinary precision where the deviations of new physics would be tiny. The W boson mass deviation, 76 MeV out of 80,000 MeV, is 0.1%. The muon anomalous magnetic moment deviation, 251 times 10 to the minus 11, is 25 parts per billion of the total value. These are extraordinarily small deviations that require extraordinarily precise measurements to detect. What lies beyond the Standard Model is the most important open question in particle physics. The anomalies I have described are the most promising current hints. They are uncertain, contested, and possibly illusory. But they are also the data we have, and the data is pointing, however tentatively and however ambiguously, towards something that the Standard Model does not describe. If this changed how you think about the Standard Model and its limits, if the W boson mass puzzle looks different after understanding the full landscape of precision tests, tell me in the comments. Tell me which anomaly you find most compelling and why you think it is more or less likely to survive as more data is collected. Tell me whether you think the null results at the LHC have ruled out the most natural extensions of the Standard Model, or whether you think the new physics is simply hiding at scales or in processes that the current experiments have not yet accessed. And subscribe if you want to stay at the frontier where the most precise measurements in the history of science are probing the edges of the theory that describes everything we know, looking for the crack that leads to what we do not know yet. The Standard Model was completed in its essential form in the 1970s. In the decades since, the primary strategy of particle physics has been to search for new particles predicted by extensions of the Standard Model. The Large Hadron Collider was built in large part to find these new particles. Let me put the LHC in context, because understanding its scale and its achievements illuminates what the null results mean. The LHC is the largest and most complex scientific instrument ever built. It is a circular particle accelerator, 27 kilometers in circumference, buried 100 meters underground beneath the border between Switzerland and Shared Tense, France. It accelerates protons to energies of up to 6.5 TeV, nearly 7 trillion electron volts, and collides them at a rate of roughly 1 billion collisions per second. The four main detectors, ATLAS, CMS, LHCb, and ALICE, record the debris from these collisions and search for new particles and interactions. The LHC cost approximately 10 billion euros to build and operates, with an annual budget of roughly 1 billion euros. It employs thousands of physicists and engineers. The data collected by ATLAS and CMS alone amounts to hundreds of petabytes. Processing this data requires a worldwide computing grid involving more than 170 computing centers in 40 countries. The first major result of the LHC, the discovery of the Higgs boson in 2012, was one of the greatest triumphs in the history of physics. The Higgs boson had been predicted in 1964 by Peter Higgs and others as a consequence of the mechanism that gives particles mass. It took nearly 50 years of theoretical development and experimental searching to find it, culminating in the simultaneous observation by ATLAS and CMS at a mass of approximately 125 GeV. Both collaborations announced a 5 sigma discovery at a joint seminar on the 4th of July 2012. The announcement was greeted with a standing ovation. Peter Higgs, then 83 years old, wiped tears from his eyes. Higgs and Francois Englert, who had independently proposed the mechanism, received the Nobel Prize in Physics the following year. Since the Higgs discovery, the LHC has been searching for the particles predicted by supersymmetry, extra dimensions, composite Higgs models, and dozens of other theories. It has found nothing. Not a hint of supersymmetry, not a sign of extra dimensions, not a resonance from a composite Higgs. The mass reach of the LHC for colored particles, particles that interact through the strong force, extends up to approximately 2 TeV for most simplified models. For weakly interacting particles, the reach is somewhat lower. The mass range that many theorists considered the most natural home for new physics, the region motivated by the hierarchy problem, and the desire for a natural dark matter candidate, has been comprehensively explored. The hierarchy problem is the theoretical motivation that drove much of the expectation for new physics at the LHC. The Higgs mass is approximately 125 GeV, but quantum corrections to the Higgs mass from virtual particles and loops are proportional to the square of the cutoff scale of the theory. If the standard model is valid all the way to the Planck scale, approximately 10 to the 19th GeV, the corrections to the Higgs mass are roughly 10 to the 34 times larger than the observed mass. To get a Higgs mass of 125 GeV, the bare mass and the quantum corrections must cancel to 34 decimal places. This extraordinary fine-tuning is what physicists call the hierarchy problem. The solution that seemed most natural to most theorists was supersymmetry. Supersymmetry pairs each standard model particle with a superpartner of different spin. The quantum corrections to the Higgs mass from loops involving standard model particles are exactly canceled by the corrections from their superpartner loops, eliminating the need for fine-tuning. For the cancellation to be natural without its own fine-tuning, the superpartners should have masses not too different from the Higgs mass, suggesting they should be accessible at the LHC. They are not there. The LHC has been running since 2010 and has searched for supersymmetric particles systematically. The simplest supersymmetric models, the ones that were most natural given the hierarchy problem, have been ruled out. The squarks and gluinos that should have been produced in abundance at LHC energies are not there. The neutralinos that should have been produced in electroweak processes are not there. The charginos are not there. The lightest supersymmetric particle, which was supposed to be the dark matter candidate, has not been found. This does not prove supersymmetry is wrong. It proves that if supersymmetry exists, its particles are either too heavy to be produced at the LHC or have properties that make them difficult to detect. Both options are possible, but both options require some degree of fine-tuning or complexity that was not anticipated in the simplest models. The natural supersymmetry that was supposed to solve the hierarchy problem is either not there or is hiding in a corner of parameter space that the LHC has not yet probed. This is the context in which the current anomalies exist. The LHC was supposed to find dramatic new physics, clear evidence for specific beyond standard model particles. Instead, it has found nothing dramatic, but it has been accumulating subtle precision anomalies at the edges of its sensitivity. The W boson mass anomaly from CDF, the muon anomalous magnetic moment, the remaining hints in B-meson physics. None of these is the dramatic discovery the LHC was expected to make, but they persist. Individually uncertain, collectively suggestive. The null results are themselves important information. The absence of supersymmetric particles at the TeV scale means the natural solution to the hierarchy problem does not work the way it was supposed to. Either the hierarchy problem is not a problem because some anthropic or statistical argument makes the fine-tuning acceptable, or the solution involves new physics that does not appear at LHC energies, or there is some other mechanism that solves the hierarchy problem without TeV scale superpartners. The null results force the field to confront these alternatives. What lies beyond the standard model is the most important open question in particle physics. The anomalies I have described are the most promising current hints. They are uncertain, contested, and possibly illusory. But the data is pointing, however tentatively, towards something that the standard model does not describe. The Large Hadron Collider is running its third major physics program, accumulating the highest energy proton collisions ever achieved, searching for direct signals of whatever is producing the anomalies. The measurements are being refined, the theoretical work is ongoing, and the standard model's extraordinary precision continues to tell us, with increasing specificity, exactly how complete it is and exactly where its completeness ends. If this changed how you think about the standard model and its limits, tell me in the comments. Tell me which anomaly you find most compelling and whether you think it will survive as more data is collected. Tell me whether you think the null results at the LHC have ruled out the most natural extensions, or whether the new physics is simply hiding at scales the current experiments have not yet accessed. And subscribe if you want to stay at the frontier where the most precise measurements in the history of science are probing the edges of the theory that describes everything we know. Now let me develop the physics of the standard model more fully, because the precision of its predictions is what makes the anomalies significant. The standard model is built on three gauge symmetry groups: SU3 for the strong force, SU2 for the weak isospin, and U1 for hypercharge. The symmetry groups determine which particles exist and how they interact. Let me unpack what this means, because gauge symmetry is one of the most important and least understood concepts in modern physics. A symmetry in physics is a transformation that leaves the laws of physics unchanged. Gauge symmetry is a local symmetry, meaning the transformation can vary from point to point in space-time. The requirement that the laws of physics be invariant under local gauge transformations forces the existence of specific force-carrying particles, the gauge bosons. For the U1 group of electromagnetism, gauge invariance requires the existence of the photon. For the SU2 of the weak force, gauge invariance requires the existence of three gauge bosons, the W+, the W, and the Z. For the SU3 of the strong force, gauge invariance requires 8 gluons. These particles are not optional. They are forced by the symmetry structure of the theory. The electroweak unification achieved by Glashow, Salam, and Weinberg in the 1960s showed that the electromagnetic and weak forces are different aspects of a single gauge theory based on SU 2 times U1. At high energies, above approximately 100 GeV, the symmetry is manifest and the 4 gauge bosons, W plus W, Z, and photon are all massless and transform into each other. At lower energies, the symmetry is spontaneously broken by the Higgs mechanism, and the W and Z bosons acquire mass while the photon remains massless. The masses of the W and Z bosons are determined by the vacuum expectation value of the Higgs field, approximately 246 GeV, and by the mixing angle between the SU2 and U1 parts of the electroweak theory, called the weak mixing angle, or Weinberg angle. The weak mixing angle has been measured with extraordinary precision by multiple experiments. Given the weak mixing angle and the vacuum expectation value, the masses of the W and Z bosons are predictions, not free parameters. But quantum mechanics introduces corrections to these classical predictions. The particles of the Standard Model continuously emit and reabsorb virtual particles, creating quantum loops that modify the apparent masses and couplings. The top quark, with its mass of approximately 173 GeV, the heaviest known elementary particle, contributes a correction to the W mass that scales as the square of the top quark mass divided by the W mass squared. This is a large correction, approximately 0.03% of the W mass, and it must be calculated precisely and included in the prediction. The Higgs boson contributes a smaller correction that scales logarithmically with its mass. Before the Higgs discovery in 2012, these corrections were used to predict the Higgs mass range. The fact that the measured Higgs mass, 125 GeV, produces corrections consistent with the precision electroweak measurements was a major confirmation of the Standard Model. The Standard Model prediction for the W mass, incorporating all the relevant quantum corrections to the highest precision currently calculable, is 80,357 plus or minus 6 MeV. This number is not a single calculation, but the result of a program of precision calculations spanning decades, involving higher order corrections in perturbation theory, resumation of large logarithms, and careful treatment of QCD effects. The uncertainty of 6 MeV reflects the residual theoretical uncertainties from uncalculated higher order terms and from the uncertainty in the strong coupling constant. The measured value from CDF 80,433.5 plus or minus 9.4 MeV is 76 MeV above this prediction. The statistical significance of the discrepancy, combining the theoretical and experimental uncertainties in quadrature, is approximately 7 sigma. This is the heart of the W boson mass puzzle. Now let me explain what a 7 sigma result actually means in the context of particle physics, because I think the significance is often overstated in one direction and understated in another. In statistics, a result at n sigma means that the probability of obtaining that result by random chance, if the null hypothesis is correct, is the area under a Gaussian distribution beyond n standard deviations. For 7 sigma, this probability is approximately 1 in 10 to the 12th, 1 in a trillion. If the Standard Model prediction is correct and the CDF measurement procedure is unbiased, the probability of obtaining a result as extreme as 80,433.5 MeV by random chance is 1 in a trillion. This sounds overwhelming, and it would be if the only question were whether the discrepancy is a statistical fluctuation. But there is a second question, whether the measurement procedure is free of systematic errors. Systematic errors are not statistical fluctuations. They are biases in the measurement that shift the result in a specific direction. The 7 sigma significance tells you the result is not a statistical fluctuation. It does not tell you it is not a systematic error. The history of particle physics contains many examples of high sigma results that turned out to be systematic errors. The Opera experiment at Gran Sasso reported neutrinos traveling faster than light at more than 6 sigma in 2011. It turned out to be a loose fiber optic cable in the timing system. The DAMA experiment reports a dark matter annual modulation signal at 13 sigma, as I discussed in the dark matter video. The physics community is skeptical because other experiments do not confirm it. The question for the CDFW mass result is not whether it is a statistical fluctuation, which it clearly is not, but whether there is a systematic error that the collaboration did not identify. The comparison with ATLAS and other experiments provides important context. ATLAS, using a different detector, different collision system, and different analysis methods, finds a value consistent with the standard model. If both CDF and ATLAS were measuring the same physical quantity without systematic errors, they should agree. They do not agree. The discrepancy between CDF and ATLAS is itself a 3 sigma result. Something is different between the two measurements, and the question is what? Let me describe the specific systematic effects that have been discussed as potential explanations for the CDF result, because understanding them illuminates how precision measurements work and why they are so challenging. The first is the Parton distribution functions. When a proton collides at the tevatron, the collision is actually between a quark or gluon inside the proton and a quark or gluon inside the antiproton. The W boson is produced by the annihilation of a quark and an antiquark. The probability of finding a quark or antiquark with a specific fraction of the proton's momentum is described by Parton distribution functions, or PDFs, which are measured from other experiments and parameterized using QCD. The PDFs enter the W mass measurement because they determine the distribution of W boson momenta produced in the collision. The W mass is extracted from the distribution of the measured lepton momentum, and the translation from lepton momentum distribution to W mass depends on the assumed PDFs. Different PDF sets give slightly different W mass values. The CDF analysis used specific PDF sets and estimated the associated uncertainty. Critics have argued that the PDF uncertainties may be underestimated. The second systematic is the energy calibration. The W mass is measured from the transverse momentum of the electron or muon produced in W decay. The energy scale of the electron measurement and the momentum scale of the muon measurement must be calibrated with high precision. CDF calibrated the energy and momentum scales using Z boson decays, which are well measured and have a mass known from LEP. The calibration procedure has been validated extensively, but residual calibration errors at the 0.01% level could shift the W mass by tens of MeV. The third systematic is the modeling of the W boson production and decay, including the effects of soft QCD radiation, multiple Parton interactions, and the transverse momentum distribution of the W boson. These effects modify the shape of the lepton momentum distribution and must be modeled accurately. Errors in the modeling can shift the extracted W mass. The advocates for the CDF result argue that all these systematics have been carefully evaluated and that the published uncertainty captures the residual errors. Independent theorists who have examined the CDF analysis have found it to be careful and thorough and have not identified a specific systematic error of sufficient magnitude to explain the discrepancy. But the consistency of other measurements with the standard model makes the CDF result an outlier, and the absence of a specific identified systematic does not mean one does not exist. RI groups determine which particles exist and how they interact. Every force is mediated by gauge bosons, particles that carry the force. Photons carry electromagnetism. W and Z bosons carry the weak force. Gluons carry the strong force. The Higgs field is the mechanism by which all massive particles in the standard model acquire their masses. In the symmetric phase of the electroweak theory, the W and Z bosons are massless, like the photon. When the Higgs field acquires a vacuum expectation value, a non-zero value in the ground state of the universe, the symmetry is spontaneously broken. The W and Z bosons acquire mass by coupling to the Higgs field. The photon remains massless because it couples to a combination of fields that is preserved by the spontaneous symmetry breaking. The mass of the W boson depends on the Higgs field vacuum expectation value and on the gauge coupling constants of the electroweak theory. But at the quantum level, these classical relationships are corrected by loops, Feynman diagrams in which virtual particles are produced and annihilated in the vacuum. The top quark, with a mass of approximately 173 GeV, contributes corrections that scale as the square of its mass, making it by far the most important quantum correction to the W boson mass. The Higgs boson contributes corrections that scale logarithmically with its mass by measuring the top quark mass to 0.1% precision and the Higgs boson mass to 0.2% precision, and by measuring the other electroweak parameters precisely. The W boson mass can be predicted to better than 0.01%. This level of precision makes the W boson mass one of the most powerful tests of the internal consistency of the Standard Model. The Tevatron at Fermilab was the world's most powerful accelerator from 1987 until the LHC turned on in 2010. It collided protons with antiprotons at a center of mass energy of up to 1.96 TeV. The CDF and D0 experiments at the Tevatron accumulated the world's largest samples of W boson events, with the full CDF dataset containing 4.2 million W bosons reconstructed in the decay channel to electrons or muons. The W boson mass measurement from CDF is based on measuring the transverse momentum of the electron or muon produced in W boson decay and comparing the distribution of these momenta to theoretical predictions that depend on the W mass. The measurement requires exquisite control of the detector's energy and momentum resolution, the modeling of the W boson's production and decay, and the effects of multiple collisions occurring simultaneously. The CDF collaboration spent years developing the techniques for this measurement and validating them against independent data. The result they obtained, 80,433.5 MeV with an uncertainty of 9. 4 MeV is higher than the Standard Model prediction by 8 sigma when the total uncertainty is considered, or 7 sigma when the theoretical uncertainty in the prediction is folded in. The measurement is internally consistent. The result obtained from the electron channel agrees with the result from the muon channel, and different subsets of the data give consistent results. The most recent ATLAS measurement, 80,360 plus or minus 16 MeV, is based on 14 million W boson events from LHC, run 2 proton-proton collisions at 7 TeV center of mass energy. The ATLAS measurement uses different detector technology, different collision type, and different analysis methods. Its central value is 73 MeV, lower than CDF, and consistent with the Standard Model prediction of 80,357 MeV. The 73 MeV difference between CDF and ATLAS is approximately 3 sigma when combined errors are considered. This is a significant discrepancy between 2 high-precision measurements, and it suggests that at least one of them has a systematic error not captured in the quoted uncertainty. The history of W boson mass measurements is instructive. The 4 LEP experiments at CERN, operating in the late 1990s and early 2000s, collectively measured the W mass to be 80,376 plus or minus 33 MeV, consistent with the Standard Model. The D0 experiment at Fermilab, CDF's neighbor and competitor, measured 80,375 plus or minus 23 MeV. The CDF measurement before the 2022 analysis had found 80,387 plus or minus 19 MeV. All of these are consistent with each other and with the standard model. The 2022 CDF result is an outlier compared to the entire history of W boson mass measurements. This does not mean the 2022 CDF result is wrong. Systematic errors that were present in earlier analyses might have been eliminated in the more careful analysis. The larger dataset might have revealed a genuine effect that was hidden in smaller samples. But the outlier status of the result, relative to a long history of consistent measurements, is a legitimate reason for skepticism. The muon anomalous magnetic moment, often written as G-2 for the muon, is a more complex story that has been developing for 2 decades. The magnetic moment of a particle in Dirac's theory of quantum mechanics is exactly G equals 2. The anomalous magnetic moment is the deviation of G from 2, expressed as A divided by 2 equals G minus 2 divided by 2. For a free electron, or muon, the standard model predicts a specific non-zero value of A that comes entirely from quantum loop corrections. The precision of the standard model prediction for the muon anomalous magnetic moment is limited primarily by hadronic contributions, the effects of quarks and gluons in quantum loops. The leading hadronic contribution, called hadronic vacuum polarization, involves a quark-antiquark loop connected to the photon propagator. This loop cannot be calculated perturbatively because it involves quarks at low energies where the strong coupling constant is large. 2 methods are used to evaluate it. The data-driven method uses experimental measurements of the rate of electron-positron annihilation into hadrons at low energies, combined with a dispersion relation to extract the hadronic vacuum polarization contribution. This method has been used for decades and gives a specific value that leads to a 4 sigma discrepancy between the measured and predicted muon anomalous magnetic moment. The lattice QCD method directly computes the hadronic vacuum polarization contribution by simulating QCD on a 4-dimensional space-time lattice. The Budapest-Marseille-Wuppertal collaboration published a lattice result in 2020 that was 2.1 sigma higher than the data-driven result and consistent with the measured value of the muon anomalous magnetic moment. If the BMWC lattice result is correct, the discrepancy between theory and experiment is reduced to approximately 1.5 sigma, no longer significant. The community is actively working to resolve the disagreement between the 2 methods. The CMD3 experiment at Novosibirsk published new measurements of low-energy electron-positron annihilation in 2023 that are inconsistent with the older data that dominates the data-driven calculation. The CMD3 result, if correct, shifts the data-driven prediction closer to the lattice result and closer to the measured value. The tension between different experimental data sets for the hadronic vacuum polarization is itself a significant puzzle. The Fermilab muon G2 experiment is expected to publish its final results from all 4 years of running in the near future. These results will have approximately 4 times smaller statistical uncertainty than the first published result, potentially clarifying whether the discrepancy is at the 3 or 4 sigma level or whether it has moved. But resolving the theoretical controversy will require either the lattice calculations to be confirmed by independent methods or the discrepancy between the CMD3 and older data on low-energy hadron production to be resolved. What would new physics look like if it is responsible for any of these anomalies? For the muon anomalous magnetic moment, new particles that couple to muons and contribute to the magnetic moment at loop level would shift the prediction. Specifically, a new heavy neutral gauge boson called a Z prime that couples specifically to muon number would contribute a positive correction to the muon anomalous magnetic moment. The mass and coupling of such a particle are constrained by the magnitude of the correction needed. For the W boson mass anomaly, new particles that contribute to the radiative corrections which shift the prediction. A new fermion with specific quantum numbers under the electroweak gauge group could shift the W mass upward. Oblique corrections, the contributions of new particles to the gauge boson propagators, parameterized by the S, T, and U parameters, can shift the W mass while remaining consistent with other electroweak precision tests. One model that has attracted attention since the CDF result is a model with an additional scalar particle that mixes with the Higgs boson. If there is a second Higgs-like particle with a mass around 300 GeV, the mixing between the two states can shift the W mass upward relative to the standard model prediction. This model also predicts specific signatures at the LHC that have not yet been excluded. The question of whether any of these theoretical models is the right one is not going to be answered by more precision measurements of the W mass alone. It requires direct searches for the new particles at the LHC or at future colliders, and consistency checks across multiple precision observables. This is why the current situation, with anomalies pointing in different directions and theoretical models that explain some but not all of them, is fundamentally different from the clean discovery of a new particle. I want to close with a reflection on what the current state of particle physics means for the future of the field. The discovery of the Higgs boson in 2012 completed the standard model. Every particle predicted by the theory had been found. The LHC had done what it was designed to do, confirm the theory. What the LHC was also designed to do, discover new physics beyond the standard model, it has so far failed to accomplish. This failure has generated genuine uncertainty about the future direction of the field. The new particles that many theorists expected to see at the LHC were motivated by theoretical arguments. The hierarchy problem of why the Higgs mass is so much lighter than the Planck scale, the desire for a natural dark matter candidate, the expectation that new physics would appear at the TeV scale. The LHC has thoroughly explored the TeV scale and found nothing beyond the standard model. The theoretical motivations for the expected new physics must be revised. The anomalies I have described offer a different path forward. Not the discovery of particles at a specific energy scale motivated by theoretical prejudice, but the emergence of patterns in precision measurements that deviate from the precise predictions of the standard model. This path is harder to follow because the deviations are small and the systematic uncertainties are comparable to the signals. But it is the path that the data is offering, and it may eventually lead somewhere. The Large Hadron Collider is accumulating more data at higher energies in Run 3. New precision measurements of the W boson mass, the muon anomalous magnetic moment, and B-meson decays will continue to be published. Future colliders, including the proposed FCC at CERN and the ILC in Japan, would allow even more precise measurements of W boson properties and direct searches for new particles. The particle that should not exist may turn out to be an artifact of systematic effects in the CDF detector, or it may be the first glimpse of the physics that lies beyond the most successful theory in the history of science. The answer is coming. The measurements are converging, and the standard model is waiting to see whether its 7 sigma crack is real or illusory. If this changed how you think about the standard model and its limits, tell me in the comments. Tell me which anomaly you find most compelling and whether you think it will survive as more data is collected. Tell me whether you think the null results at the LHC have ruled out the most natural extensions of the standard model, or whether you think the new physics is simply hiding at scales or in processes that the current experiments have not yet accessed. And subscribe if you want to stay at the frontier where the most precise measurements in the history of science are probing the edges of the theory that describes everything we know, looking for the crack that leads to what we do not know yet. The pattern across these anomalies, the W boson mass from CDF, the muon anomalous magnetic moment at Fermilab, the remaining hints in B-meson physics at LHCb, is worth examining as a whole because individual anomalies can be dismissed more easily than patterns. Every one of these anomalies involves measurements that are harder to perform and to control systematics for than typical LHC searches. The W boson mass requires understanding the detector's response to the lepton momentum to better than 1 part in 1,000. The muon anomalous magnetic moment requires knowing the muon's momentum in the storage ring to parts per million. The B anomaly measurements require precisely modeling the production and decay of B-mesons in a hadronic environment. In each case, the challenge is not detecting the signal, but controlling the background and the systematic effects. This is the nature of precision physics in the modern era. The standard model is so good that to test it, you have to measure things to extraordinary precision where the deviations of new physics would be tiny. The W boson mass deviation, 76 MeV out of 80,000 MeV, is 0.1%. The muon anomalous magnetic moment deviation, 251 times 10 to the minus 11, is 25 parts per billion of the total value. These are extraordinarily small deviations that require extraordinarily precise measurements to detect. The fact that anomalies at this level of precision are appearing now rather than 20 years ago reflects the maturation of experimental techniques to the point where these measurements are possible. The CDF collaboration worked for years to achieve the precision of the 2022 W mass measurement. The Fermilab muon G2 experiment was designed and built specifically to test the Brookhaven anomaly at higher precision. This is not accidental data that turned up anomalous. These are deliberate, carefully planned programs of precision measurement aimed at testing the standard model at the frontier of what is experimentally possible. The fact that anomalies have appeared at this frontier and that they have not immediately dissolved with better statistics is a signal worth taking seriously. Not as confirmation of new physics, which requires more than currently available, but as an indication that the standard model may be reaching the limits of its domain. The standard model was built in the 1970s without knowing the mass of the Higgs boson, without knowing the mass of the top quark, without knowing the precise value of the strong coupling constant. All of these were measured later and found to be consistent with the theoretical framework. The theory was robust enough to accommodate the measurements. But the theory was not designed to accommodate measurements at the 0.01% level in quantities that depend sensitively on all the parameters simultaneously. What lies beyond the standard model, if anything does, must be consistent with every precision measurement made so far at the level of their precision. This is a very tight constraint. The W boson mass anomaly, the muon anomalous magnetic moment, the B anomalies, if any of them is real, must be explained by new physics that also passes all the other tests. The space of theories that can do this is small but not empty. Finding the right theory will require either discovering a new particle directly or accumulating enough precision anomalies that the pattern becomes unmistakable. Both paths are being pursued. The LHC Run 3 is providing more data. The high luminosity LHC, beginning operations in the late 2020s, will accumulate 10 times more data than all previous LHC runs combined. New precision experiments are being planned and built. The particle that should not exist is waiting to be found or to be explained away. The most precise theory in the history of science is running out of places to hide.